First of all, you don't have to heat your metal as much, so in terms of oxidation, it's less of an issue. But also if you reduce your melting point, your heat transfer is not as chaotic with the mold. So the lowest temperature you can get for casting, the better it is. There's no doubt about that. So this one here, you can see the metal is fed through the center, and then it's going all around, and you can form patterns that are very complex. It doesn't mean that you don't do a final machining for the appearance. I mean, mag wheels, sometimes it's just like perfect finish, a very shiny finish. But for efficiency, it's the idea of making this very intricate pattern very rapidly, because we're looking here at metallic molds. I will bring, so the same way when we talked about jewelry, I talked a little bit about porosity. Porosity is a big issue with castings. Here I'll talk about residual stressors, because the way you come and solidify here, you have a very thin section, you have a thicker section. You know for sure it's not going to solidify at the same rate, and the last one to solidify is going to be pulling on other components that are already solidified. The one example of this that I can use, and it's a project that we had last year, is we were looking just as a glass bottle. It's very simple. You have that in the lab every day. If your bottom is much thicker, this is just glass. So you put glass in a mold, you spin it around with different axes, and you get it to solidify. If this thickness is much higher, and it's just in contact with the same mold here, material, you almost know for sure that this will become completely solid before you solidify through the thickness here. So this is going to take a lot more time than this wall, and it will try to reduce the diameter. So you get a lot of bending stresses in those corners that can initiate cracks if this is not tempered or doesn't have anything special added to it. So the same effect is applicable to the wheel here, even though the geometry is more complex. I think you can understand there'll be some sections that will take longer, and they'll activate a spring because everything else is already stiff. It happens in welding. The reason I mention it is we had a few projects with aluminum wheels with fatigue cracks. And if you take the wheel and do a very detailed computer analysis of it, you'll find the stresses are very low, and there shouldn't be any problem. So you need to think about these residual stresses to explain why cracks can start improperly. This is going a little beyond today, but one easy way to go around it is to heat treat the casting after the fact to reduce these residual stresses. And you could do that with that bottle as well. You just heat it up at a temperature where it will relax. It's still a solid, but it will relax and relieve the residual tension and compression. So that's, we call it a stress relief. And it has to be obviously below most transformation temperatures. So a lot of times it doesn't have bad consequences, but it is an extra manufacturing step, and therefore it's not done all the time. The last process I want to introduce to you is this semi-solid casting, and we already talked about it on Friday when I was talking about the big billet coming off the continuous casting, and you're using a magnetic field to spin it around and break the dendrites. Well, semi-solid casting is exactly that. So if you have normally dendrites, like on the left-hand side, you can essentially optimize your process to either form the dendrites and break them down, or just essentially come with a feedstock that only partially melt. The way I've seen these runs of semi-solid casting is you use a die casting machine But when you heat up, you don't heat up the whole composition, so your billet is already prepared to be a slurry, and you inject it really fast. So all you have to do is make a little bit something similar to this on the first place, and then you don't heat up completely, so it stays as a solid. It reduces the shrinkage. There's normally a reduction in volume when you go from the liquid to the solid. If you already say 40% solid, then you're reducing the shrinkage by that much. So there are a lot of advantages, and in terms of nucleation sites, they are everywhere. You already have a lot of solids available for the solidification. There's still segregation, because you can see on the image the composition is not the same, but it's more distributed throughout the part as opposed to being at one specific location. So it's a very interesting technology. Obviously, there's more money involved in making the feedstock that will get into your mold. And therefore, it's not the largest casting production volume, that's for sure. So we went through the details of solidification, talking about that if it's homogeneous, it's very different than when you're dealing with a real situation where you already have a crystal or you have impurities in your melt that will allow for this to happen without needing that critical volume. We talked about segregation, that it's coming right off the phase diagram, and what happens with how fast you cool will only affect if you're going to form these dendrites and how big they're going to be and all that stuff. So for casting, I talked about gravity sand casting, so these were the fittings. Centrifugal casting, we talked about spinning it around and trying to control the flow as you go outward. The die casting was a wheel example. And semi-solid casting, yeah, is just a better way to do a die casting or a detailed casting for reduced shrinkage and a more homogeneous microstructure. What I want to do, because we have a few minutes, is just go a little bit over what we're doing next. We have this big casting, so it's an ingot, for example, and we have the outer skin zone that was chilled. We have our columnar grains, and then we have more aqueous zone in the middle. So just me here, very fine grain here. The only way that you can take this, so your composition is, if you look at most alloying element, the composition from here to here, from this to the center, is going up. The alloying elements to the dead center right here, and it's really something you want to avoid for most products. If I give a machinist the instruction to make me a part, very detailed part, he doesn't want to have to ask me necessarily, well, you know, I got this big ingot here, is it okay if I machine it here, if I machine it there? And I'm going to have a different composition, completely different properties. So there is a large need to simplify and homogenize this microstructure, and that is by hot deformation processing. What the hot deformation processing is going to do is allow for diffusion. It will allow for diffusion because you're hot, but also because you're deforming. Deformation itself favors the movement of the different atoms to get the microstructure more homogeneous. What I think you'll find helpful in the next lecture is we're going to talk about grains in material, but in that context. What happens to the grain and what we can do with grains through that hot temperature deformation process. And I'm not going to go crazy with dislocations. I know you're not necessarily all course 3, and even in course 3, not everybody likes it the same way, but we'll have to talk about it in a general sense because it does come into play. Anytime that you deform a metal, you will generate more dislocations into it. And the advantage of being at high temperature is you can recover more of these dislocations. So when we do hot rolling, and I'll try to get you a good video of it, you can get in a situation where your density of dislocation stays about the same, because you're producing them and then you annealing them at the same time. And same for the grains. You keep making new grains and growing grains, but shrinking grains, and then overall you become to that steady state where things keep moving, but they're not, if you take a snapshot, they're relatively the same. So that's how you go from a very large diameter billet to a bar. And one example of bar, the shop that my friend was working at was just leaf springs for pickup trucks and trailers and stuff. You don't want any problem with it. You can't just go and have these columnar grains. It needs to be high quality everywhere. And even if you're looking with the independent suspension and four wheels, which most little SUVs have, you still have these coil springs that need to be very good quality everywhere, because you don't know exactly where the highest stress is going to be. It needs to be good all around. So from going to here is going to be the first half of Thursday's lecture, essentially. Professor, you got anything that you'd like to say about tomorrow, or?
No, but I do want these, I want the other one of these. I didn't tell you, it's 6% precious metal.
I was gonna ask you, what metal is it?
It's, it is a single crystal, obviously, and the typical single crystals they were using at this time were, I can't remember the name. They're a bunch of letters and then a 4 and 5 alloy, and they're typically 6% rhenium, which is a platinum group metal. So I like to keep them.
You can make your pattern that you will cast these blades with holes in it for air circulation.
I'll show you one of those tomorrow.
That's good.
Yeah, and those blades are worth about $7,000 a piece. Partly because they got about $1,000 worth of metal in them.